Okay, so a big question that I have completely not answered yet at all is the question of how do we calculate area under a function when the graph is not a straight line? And so to answer this, I'm going to start with an example. And the example that we're going to look at is the graph of y equals x squared. Now you can double check this on your calculator, but the graph of y equals x squared is a parabola. Kind of touches the x-axis right here at 0, 0 and bounces off. And I'm using this as an example rather than the more complicated function about our rate of change of the amount of coal being produced to start with. We'll get back to that one later. Okay, so we have y equals x squared, and let's say that we're interested in finding the area under y equals x squared from x equals 0 to x equals 1. Okay, so in this picture, here is x equals 0, and maybe here is x equals 1. And so the area that we're talking about, I'm going to draw a vertical line. Now at x equals 0, that's where the graph touches the x-axis, so I don't really have much of a vertical line there. But the area that I'm talking about is this shaded region under the graph, above the x-axis, and between an x value of 0 and 1. Okay, now this area can be represented with the following notation. Long stretched out s, you've seen that before, x squared dx. You've seen a function in the middle, you've seen the dx at the end. I'm going to throw in two numbers on this long stretched out s. A 0 and a 1, meaning the starting x value at the bottom and the ending x value at the top. And this is an example of a definite integral and this is called a definite integral because there are numbers on the integral sign. The ones that we talked about in the last class and the class period before that were indefinite integrals, which meant find the antiderivative, and that's what you're doing. Here, if I throw numbers on this long stretched out s, we read this as the integral from 0 to 1 of x squared dx. And this integral represents the area under the function that's written in the middle, starting at the bottom x value and ending at the top x value. So if I were gonna write this in general, if I had a random function, and here is my random function, there it is, y equals f of x. And let's say that I cared about the area under this function starting at an x value of a and ending at an x value of b, and I wanted to know this area right in here. The way that I would write that is this area under our function starting at x equals a and ending at x equals b would be the integral from a to b of f of x dx. Okay? So that's our example of a definite integral. And then there's this question of how to evaluate something like that. And so I'm going to tell you about that, how to evaluate a definite integral. Well, the way we evaluate a definite integral is we write down the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F of x is any antiderivative of little f of x. Okay, there's a lot of symbols going on there. Let's talk about what they mean. By the way, this thing that I've just written down here, it turns out this is a really big result in calculus. It is such a big result that this thing inside the box here is called the fundamental theorem of calculus. So there's a lot of stuff that goes into this theorem, but we're just going to go with it now. So let's use this fundamental theorem of calculus, this instructions on how to evaluate a definite integral, and go back to our example of find the area under y equals x squared from 0 to 1. Okay, so our area is the definite integral from 0 to 1 of x squared dx. And what the fundamental theorem of calculus says is it says that the first thing we're going to need to do is to find an antiderivative. So the way that I'm going to work with this is I'm going to do some work off to the side and look at the indefinite integral . So I'm going to look at this definite integral and I'm going to ignore the numbers on the bound, I call them the bounds, and just look at the integral of x squared dx. Okay. Without those numbers on the long stretched out s, I know how to deal with this. I can find the antiderivative, and the way we find the antiderivative of x squared is we add 1 to the power, and we divide the number in front, which is a 1, by the new power. So I have 1/3 x to the third plus c. Okay, our instructions down here say where capital F is any antiderivative. Here's an antiderivative for x squared, and it can be any antiderivative, so I'm going to pick the antiderivative where the plus c is 0. So my capital F of x is 1/3 x cubed. Okay. Now my instructions say use that antiderivative and plug in the top number and plug in the bottom number. So I'm going to calculate f of my top number. So this is like f of b, so f of 1, capital F of 1. Everywhere I see an x, I'm going to replace it with 1, so I have 1/3 times 1 to the third. And if I multiply that out, I get 1/3. And capital F of A is like my bottom number. So I have capital F of 0, which is 1/3 times 0 to the third, which is equal to 0. Okay? Okay. The fundamental theorem of calculus says find the antiderivative, plug in the top number, plug in the bottom number, and subtract. So f of b, which is capital F of 1, minus capital F of a, which is capital F of 0, is going to be 1/3. That's this guy, minus 0, which is 1/3. So our area, the integral from 0 to 1 of x squared dx, is equal to 1/3. So that says this area right here inside this kind of triangle-ish shape, that area is equal to 1/3 square units. Okay, so this is our first example of evaluating a definite integral, and a definite integral tells us the area under a function starting at one x value and ending at another x value. Okay, let's look at another example. Okay, in this example, we would like to find the area of the shaded region. And so we're given a picture. And we have a picture of a function. It looks kind of like this. And the formula for this function is f of x equals 1/2 x squared plus x plus 1. And then we also are given some marks on here. So we have -1, -2, and -3. And on the other side we have 1, 2, 3. Okay. We also have a vertical line at x equals -2 and a vertical line at x equals 1. And the region that is shaded is the region under our graph and above the x-axis between x equals -2 and x equals 1. So we want to find this area right here. We want to find a value for that area. I mean, you might think of this as, hey, I have a really funny looking wall outside and I need to know how much paint I need to buy, so I need to know what the area is that I want to paint. Or you can just think of it as, yeah, we want to find the area under this function, remembering that eventually that will come back to figuring out how much coal is produced, and we'll also answer quite a few other questions later on. Okay, so to find this area, we can write down that the area is written as the definite integral from -2, that's our lower bound, up to 1, which is our upper bound, our x values. Our function is 1/2 x squared plus x plus 1. And then we have that dx at the end because an integral sign is always paired with a dx at the end. Okay, so if we can evaluate this integral, we'll know what the area of this shaded region is. All right, to evaluate a definite integral, I always start with the indefinite integral. So we have the integral of 1/2 x squared plus x plus 1 dx. And the integral sign and the dx say find the antiderivative of the function in the middle. So I can add 1 to each power, so I can add 1 to the first power, so I have x to the third, and then the number in front divided by the new power, so I have 1/2 over 3 x to the third, plus, when I add 1 to the power here, my power on the x was a 1, so now I have x squared, and I divide the number in front by my new power, so I have 1/2 x squared, and the antiderivative of a number is that number with an x tacked on. And then I always have a plus c whenever I do an indefinite integral. Okay, so this is our antiderivative. I'm going to clean up this fraction at the beginning. You can either do this by hand or you can do this in your calculator. I did post on our website, if you're not familiar with the fraction button in your calculator, there's a video there, you should check it out. But 1/2 divided by 3 is 1/6, so we have 1/6 x to the third plus 1/2 x squared plus x plus c. Okay, everything except for the c is our capital F of x. And what we're going to do is we're going to plug in our top bound and our bottom bound into our capital F function, and then we're going to subtract them. So we'll start by plugging in the top bound. So capital F of 1 will be 1/6 times 1 to the third plus 1/2 times 1 squared plus 1. Okay. Now, I went ahead and typed that into my calculator, and when I did, I came up with 1.67. Most of the time, at least for this class, when we're evaluating definite integrals, our final answers are going to be in terms of decimals. So once you are evaluating your antiderivative, once you're plugging your bounds into your capital F function, you can get a decimal answer, and that's totally fine. Okay, so that's capital F of 1, and now I'm going to plug in the bottom bound. Capital F of negative 2 will be 1/6 times negative 2 to the third plus 1/2 times negative 2 squared plus negative 2. And you want to be really careful on plugging in these negative values. Make sure that you put negative 2 in parentheses, because if you don't, that square won't cancel the negative sign. Okay, so when you type all of that into your calculator, and you should double check this, you should get negative 1.33. Okay? All right. So to evaluate our definite integral, we first find the antiderivative, then we plug in the top number, plug in the bottom number, and subtract. So capital F of the top number minus capital F of the bottom number is going to be 1.67 minus, okay, our bottom number was negative 1.33. So we have 1.67 minus a negative 1.33. And if you do that math, you can do that in your calculator if you want to, you end up with a final value of 3. So all of that work just told us that the area of this shaded orange region right here is 3 square units. Okay, so to evaluate a definite integral, we find the antiderivative, plug the top number into the antiderivative, plug the bottom number into the antiderivative, and then subtract them. And whatever we get for that final number, that's the area of this region. Okay. Now that's evaluating a definite integral by hand. I want to point out a few features on your calculator that are helpful in terms of checking your final answer. Now when it comes to working on your remote assignment, or in terms of any time that you're evaluating these integrals, most likely you will be asked to evaluate these integrals by hand, so you need to show your work for those. But here's a good way to check your final answer. Okay, so one way to check your answer is to graph the function that you're trying to find the area underneath. So I can graph 1/2 x squared plus x plus 1, and maybe I'll make sure that my window is reasonable. What we care about is we care about x values from -2 to +1. Maybe I'll try and draw the same window that I have up given in the picture. So maybe from -3 to +3. And then we'll do a zoom fit and see what happens. Okay, now here is our picture. Notice how this graph hits the bottom of my window, but the one up on the board did not. I might change my window here. What I notice here is that the y minimum is 0.5, so maybe I'll make that a 0 so I can see the x-axis. Okay, once I have my function graphed, this is the important part. So if I do second and then trace, that gives me calculate. So second, trace, and what you might notice is now you can go down to number 7 and you might recognize that integral sign, the integral of f of x dx, and that's what we're looking for. And so I hit enter, and the calculator asks me for the lower limit, and that lower limit is the number on the bottom of the integral sign. So in this case, that's -2. And then we are asked for the upper limit, which is the number at the top of the integral sign. So in our case, that's a 1. So I type in the 1, and this tells me, first of all, it shades the region for us, which is pretty cool. It says the integral of f of x dx is equal to 3, and it tells us down below that your lower bound is -2 and your upper bound is 1. Now, My regular graphing calculator is a little bit older. It doesn't have that bound in there, the -2 up to 1. It just tells me the integral of f of x dx equals 3. But nonetheless, it gave us the same answer that we came up with by hand. All right, in our final section, we're going to do another example, but we'll pause the video here. Thanks for listening.